anatomists and physiologists. This is another video in our urinary system series. Today we're talking about how urine is formed. As a reminder, the nephron, which is the functional unit of the kidneys, the thing that does the kidney's job, which includes making urine, right? It happens at the nephron. So this diagram is showing you generally how the nephron works, which is three major processes. And so number one is glomerular filtration. Like at the glomerulus, we produce filtrate. Some of that filtrate is pushed back into the blood. That's called tubular reabsorption. And then some of that content from the blood is pushed back into the nephron. That's called tubular secretion. So we'll go through all of those. All of this works, though, to form urine. So the end product is urine, which is then sent down out of the nephron, out of the renal pyramid, out of the minor and the major calyces, into the renal pelvis, down the ureters, bladder for storage. You get the point, right? So it's all connected. Okay, so let's start at the beginning, which is the renal corpuscle. And the renal corpuscle consists of the glomerulus, this whole thing, we talked about it as a Lego hand, with the podocytes, but then also the blood vessels that those podocytes cover, which is called the glomerulus or glomerular capillaries. And remember that these capillaries are really leaky, but the podocytes help make sure that it's leaky in just the right way. Podocytes, those are the feet cells that have these little teeny tiny processes that form filtration slits, right? So we keep in the blood all of the blood cells, the plasma proteins, macromolecules, that kind of thing. But the small stuff like water, glucose, amino acids, nitrogenous wastes, all of that stuff enters the glomerular capsule into that capsular space, which is just the space in that Lego hand. And that's ultimately what will enter the proximal convoluted tubule, the first part of the nephron, like the tubby part. A lot of what motivates substances to leave the blood and enter that glomerular capsular space or not is based on pressures, how hard that fluid is pushing on the walls of these vessels, but also how strongly the colloid osmotic pressure is pulling on everything. So let's take a look at that. So a lot of what motivates substances to leave or not leave the glomerulus are based on pressures, how hard fluid is pushing on the walls of the vessels, and how strong the colloid osmotic force is. These aren't new terms to us because we discussed these terms when we were back in capillary exchange, back in the blood chapter in blood vessels, but let's talk about them again. Okay, so we have hydrostatic pressure. Hydrostatic pressure is how hard the fluid is pushing on the walls of the vessels. So how hard fluid pushes on vessel walls. And this can come from inside in the glomerular capillaries, and we can abbreviate that to hydrostatic pressure of the glomerular capillaries, HPGC. So that's the pressure here. From inside the glomerulus, how hard is that blood pushing on those walls? But we also have hydrostatic pressure in the reverse. We have in the glomerular capsule, how hard is that fluid pushing on the walls of the glomerulus? And that's called the hydrostatic pressure of the capsular space. And this is abbreviated in our image here of called HPCS. So that's this one here. I'll zoom in on this in just a sec. Okay, but we also have osmosis happening, the forces of osmosis. Inside the blood, there's plasma proteins, and the plasma proteins stay inside of the blood due to the actions of the filtration membrane. So that, remember, like solutes, like proteins, like plasma proteins, draw water toward them by the process of osmosis. So if that means that there's an inward force pulling water towards the inside of the glomerular capillaries because of the plasma proteins. So this osmotic pressure is OP, and that's of the glomerular capillaries. And this is plasma proteins draw water. All of this leads to something called net filtration. So we have fluid osmotic pressure. All of that leads to net filtration pressure, NFP. And I think of this as like how much filtration is happening with all of these forces at play. And there's a difference between the pressures pulling fluid out and the pressures pulling fluid back in. So since the outward pressures are seen, which are seen in this picture here, let me zoom in. So if we're thinking about net filtration pressure, notice how the size of the arrows are proportional, right? So there's more force pulling stuff out compared to forces pulling stuff in. Okay, so this is the hydrostatic pressure within the glomerulus, and these two are forces pulling stuff inside, the osmotic pressure and the hydrostatic pressure within this capsule. But these are smaller forces, right? So overall, we're forming filtrate. And that filtrate is entering the PCT and then the rest of the nephron. So if there's a certain amount of filtration pressure, filtration happening, how we measure it is called glomerular filtration rate, or GFR. This is a measure of how much filtrate is formed not by a single glomerulus, but by all the glomeruli. So how much filtrate is formed by all the glomeruli in 1 minute. GFR that's bigger, like a bigger number of GFR, that means that there's more filtration happening, and then a smaller number would mean that filtration is happening less. There's a few factors that affect GFR, so let's talk about those. One of them is called NFP, net filtration pressure. This is the hydrostatic pressure of the glomerular capillaries. And think of like hydrostatic pressure like blood pressure, right? Blood pressure of the glomerulus. And this can be altered by changing how big in diameter the afferent arteriole is. So we can change by increasing or decreasing diameter of afferent arteriole. But also we have to think about total surface area. Total surface area for filtration, it means like how much space can we do filtration? And there's special cells that can alter this. They're called mesangial cells. That means they can increase or decrease the surface area as a surface area. More surface area means more filtration, right? But also we have to think about how permeable is that filtration membrane. If that filtration membrane is normally really, really, really permeable, so we don't have to worry about this so much. But overall, when we're thinking about GFR, overall GFR is approximately 120 to 125 milliliters per minute. If that doesn't mean anything to you, because it doesn't really to me, think about 180 liters per day. 180 liters per day of filtrate that we form. 180 liters. So that's like 92-liter bottles of soda being produced per day of filtrate. And that's not how much urine is being formed, it's about how much filtrate is being formed. But it's a really important to talk about GFR because we need to make sure that GFR is regulated so that we can make enough filtrate, produce urine, but also to preserve blood volume. So blood volume to be where it's supposed to be, GFR to be where it's supposed to be so that we can do all of the things. So how do we regulate GFR if it's so important? There's two major controls. there's this is a whole schematic from your book here. There's two major controls. There's intrinsic controls. Intrinsic controls means like that word intrinsic means within, which is the kidney doing its own regulation. I think of intrinsic controls as being comparable to like the locals. Extrinsic controls, those are extrinsic. Extrinsic controls are who comes to step in when the locals can't quite get it done. So when the kidneys can't quite get it done, then other body systems step in. Others take over. The intrinsic controls and extrinsic controls have different priorities. Intrinsic controls mean that we really just want to maintain GFR. The goal of intrinsic controls is to keep GFR constant. We want to produce, filtrate, produce urine, all the things. We don't necessarily care about what the blood pressure is of the body. We just want the GFR to stay pretty much same. And we're going to make adjustments to account for that. However, the extrinsic controls, remember these are the others, the other body systems. So the extrinsic controls care a lot more about the body system. So the extrinsic controls care a lot more about making sure that blood pressure is regulated. Systemic blood pressure is sufficient. Not too much, not too little. So let's talk about the intrinsic controls first. So when it comes to intrinsic controls, we have two major controls here. We have myogenic in the blue, and the orange is called tubuloglomerular. I'm going to zoom in first on the myogenic mechanism, the blue one. Myogenic mechanism. I think of that word myo. Myo means muscle. So we're targeting some kind of muscle there. And that makes sense because it deals with smooth muscle, okay? So when we're thinking about if that blood pressure were to fall, the systemic blood pressure, what would happen is that blood pressure in the afferent arterioles would decrease. If that blood pressure in the afferent arterioles decreases, this also decreases GFR because there's less pressure pushing blood into the glomerulus, right? When that happens, we decrease the stretch of the smooth muscle in the walls of those afferent arterioles. If that happens, then that smooth muscle in the walls is going to relax. So vasodilation, remember that's smooth muscle relaxes. If that smooth muscle in the afferent arterioles relaxes, that leads to an increase in GFR. That leads to an increase in GFR because we increase blood going to glomerulus. More blood, more pressure, more GFR. Okay, so that's the myogenic mechanism, the muscle one, the smooth muscle one. The next one is this orange panel, which is tubuloglomerular mechanism. This is autoregulation, auto meaning self, because it's the kidney doing regulation for kidney stuff. Okay, so we're starting still. Systemic blood pressure falls. If systemic blood pressure falls, this automatically decreases GFR because still there's less blood pressure. If GFR falls, this also decreases the filtrate that's being formed. If we decrease the filtrate that's being formed, we also decrease the contents of sodium chloride, salt, in the nephron loop. We know that we have cells in the juxtaglomerular complex, the JG complex. I'm going to highlight that one. And the juxtaglomerular complex, we have these cells. I'm going to highlight them in pink. They're called macula densa cells. Macula densa cells sense sodium chloride levels and filtrate. If sodium chloride levels fall because there's less filtrate, right? If sodium chloride levels fall, then we make sure that vasodilation happens because there's some chemicals that are released or not, in this case, not released. So those macula densa cells, they don't release any chemicals to vasoconstrict, so then we increase vasodilation. Vasodilation, remember, vasodilation is still smooth muscle relaxes. If smooth muscle relaxes, we're still going to increase GFR. By increasing GFR, this happens because we increase the blood going to the glomerulus. So same vibes. So those are intrinsic controls. Notice that the direct thing that happens is we increase GFR because the goal is to keep GFR constant. This is a local goal. The flip side of this, though, are the extrinsic controls. The goal is to make sure that systemic blood pressure is where it's supposed to be. There's two major mechanisms. There's a hormonal mechanism and there's a neural mechanism. I'll talk about the neural mechanism first because it's the sympathetic nervous system. So if systemic blood pressure falls, less blood pressure. If we have less blood pressure, that's the tan panel that we're looking at here. Remember that we have baroreceptors. Baroreceptors sense blood pressure because baro means pressure. If those baroreceptors turn off, that activates our sympathetic nervous system. Activating our SNS is our fight or flight one. So activating our fight or flight nervous system causes vasoconstriction. Vasoconstriction means that we contract smooth muscle of the blood vessels in the systemic arterioles. If we contract smooth muscles by vasoconstriction, then that automatically leads us to increase blood pressure. Vasoconstriction increases blood pressure. We learned this in blood vessels. So that's the neural control. We can also control our extrinsic controls to control systemic blood pressure hormonally. And we've already talked about this, right? This is the renin, angiotensin, aldosterone system. So the same stimulus, systemic blood pressure falls. If systemic blood pressure falls, we have these cells in the juxtaglomerular complex of our kidney, JG complex. And those cells are called granular cells. Granular cells sense blood pressure of afferent arteriole. If that blood pressure of the afferent arteriole falls, because, well, systemic blood pressure also fell, then this is going to activate and release this hormone called renin from the granular cells. Renin leads to a series of steps that forms the enzyme that forms the molecule angiotensin 2. Angiotensin 2 does tons of stuff. Some of the stuff that angiotensin 2 does is release aldosterone. So we increase the aldosterone release. And this is released from the adrenal cortex on top of the kidneys. What aldosterone does is it increases sodium reabsorption. So increases sodium in the blood. And if sodium leaves the nephron into the blood, then water also enters the blood. If water enters the blood, then we increase blood volume. Increasing blood volume increases how hard we're pushing on those vessel walls, thus we increase systemic blood pressure. The other thing that angiotensin does, one of the other things, is that we do vasoconstriction. So same thing, vasoconstriction, we increase blood pressure. And that's because we increase peripheral resistance. So that increases blood pressure. Notice that if blood pressure falls, the extrinsic mechanisms state that we're going to fix it. The intrinsic controls say that if blood pressure falls, we're going to make sure GFR stays the same. We're going to try to increase it as much as possible. So step one of forming urine, we already talked about, was glomerular filtration. Happens in the glomerulus. The next thing we're going to discuss, so check off, all done with that. The next thing we're going to discuss is tubular reabsorption. That's what we're going to talk about in the next set of slides. Tubular reabsorption is the act of pulling certain contents of the filtrate from the nephron back into the blood. So reabsorption here is talking about it's taking stuff from the nephron and putting it in the blood. So we're reabsorbing stuff back into the blood. And this happens in two ways, right? Substances can either be moved in there transcellularly. That word transcellular means that we're moving stuff by the process of transcytosis. Paracellularly is another way that we can move stuff back into the blood. Paracellularly means that that substance goes between cells. To move a substance transcellularly, that means that we move it across the cell. So here's my nephron tubule. And then I have a bunch of cells here, right? Let's say these are cells of the PCT, so they have those microvilli. So in transcytosis, that substance will go in through the apical membrane, across the cell, and then out. And when it goes out the other side, that's the basolateral membrane, right? And this is a lot like how we learned about how stuff moves in the digestive system for absorption. But paracellularly means that that substance is moving in between cells. And so that substance would move like, let me get a different color. I'll use purple. That means that substance would move in between those cells, and only certain things can do that. So transcytosis, that's the red one. And then paracellularly, that's this one. And paracellular routes can be only for substances that are like small enough and have the right properties. Things like calcium, magnesium, sodium, potassium, that kind of stuff. Because these cells are joined by tight junctions, so we kind of have to make sure that those things are small enough. So we can move things by transcytosis or in between cells, but that process can also be active or passive. So if it's an active process, we need ATP in some step of the process. That's the active part, right? ATP. But it can also happen passively by diffusion, osmosis, without the need for ATP. And the thing to remember here is that most tubular reabsorption mostly occurs in the proximal convoluted tubule, mostly in the PCT. Here's a summary of the transcellular route and the paracellular route in case you want to take a peek at it for your book here. We have those microvilli of the cells of the PCT. We have stuff moving transcellularly and paracellularly into the blood. Sodium plays a really important role in tubular reabsorption because the movement of sodium makes an electrochemical gradient. That's a difference in charge and a difference in concentration between the nephron tubule and the capillaries. If there's a difference in those things, then other ions are motivated to move by their charge and concentration, like chloride and bicarb, that kind of stuff. This begins due to the sodium potassium pump. So stuff is like the sodium potassium pump, that plays a big role. That's active transport, right? That causes sodium to enter the cell at the apical membrane, but it also helps with reabsorption of other stuff, like for getting nutrients. It also promotes water to move into the blood, but water moves into the blood because of special transport proteins called aquaporins. So water moves into or out of cells via aquaporins. Aquaporins are transport proteins specifically for water. If aquaporins don't exist on a cell's membrane, then water really can't move in or out of that cell. Okay, so here's a slide showing you the reabsorption of sodium and other stuff. The thing to remember here is that most tubular reabsorption happens because sodium is reabsorbed, and this is what establishes that electrochemical gradient I was talking about. So we have some stuff going on here. We have a list of steps that I think is great for you to read over. We have things going on like secondary active transport that occurs for substances like, let me write this down, secondary active transport. That occurs for things like glucose, amino acids, ions, and vitamins. And again, this happens by the sodium potassium pump. And sometimes this involves co-transporters. That means that you need a transport protein and a buddy, like a buddy to go across the membrane with. So that means you need another substance to bind that transport protein to go across the membrane. The proximal convoluted tubule contains lots of aquaporins, so it's transport channels for water. And that means that water passes through almost freely because aquaporins are there. If aquaporins are absent, water is not going to move. In some portions of the nephron, aquaporins can show up if hormones are around, like antidiuretic hormone, for example. So if aquaporins are always present on certain regions of the nephron, especially like the descending limb of the nephron, the PCT, that's called obligatory water reabsorption. If aquaporins are sometimes present, like only if a hormone is around, that's called, I ran out of space, so I'm writing it over here, facultative water reabsorption. It's not obligated to happen, but if there's a hormone or something that makes it happen, then that's good because that's what we need at that time. The other thing that happens is once water leaves the kidney tubules, that causes the water to decrease in the tubules, right? And if that happens, the substances in the ISF can also be reabsorbed because they're moving down their own gradients. Because we always go from a high concentration of a thing to a low concentration of a thing. But at some point, we start to reach this thing called transport maximum. Transport maximum, that's when the transport proteins are fully occupied for a particular substance. That means that, like, most of that substance is back into the blood. We can't put any more of it back into the blood, which means that everything left over is stuck in the filtrate. If it's stuck in the filtrate, then it'll end up showing up in the urine. That's transport maximum. This slide is showing you what each portion of the nephron reabsorbs back into the blood and also what's secreted. I think this is a really great picture to keep coming back to. But I'm going to focus for this lecture on the blue stuff. So in the PCT, this is figure 25.17, just in case you wanted to know. Okay, so what we're looking at here is we have that Lego hand of the glomerular capsule, and then we have the PCT. In the PCT, there's tons and tons of water because there's lots of aquaporins there, right? But it's also things like glucose, amino acids, other nutrients. Nearly all of our glucose is reabsorbed back into the blood because that makes sense, right? We need those nutrients. Glucose for energy, water for blood volume, all of this stuff. So we need all of this. Gets put back into the blood. And this is like 65% of our filtrate is put back into the blood. So over half of it. Then from the PCT, we go down the descending limb of the nephron loop. So going down the descending limb of the nephron loop, notice that the only thing that's moving is water. This is something that's really, really important. So the descending limb of nephron loop is only reabsorbing water. Not solutes. That becomes really, really important later. The other thing that happens is that in the ascending limb of the nephron loop, the ascending limb of the nephron loop is only reabsorbing solutes, not water. I'm going to put a star there because this is really important later. So star there and star here because we're going to talk about those later. So the ascending limb, the descending limb. The descending limb, only water can leave, not solutes. In the ascending limb, only solutes can leave, not water, okay? And then we go through the DCT, distal convoluted tubule. And in the DCT, we don't have tons of stuff going on except when we're under the influence of different hormones, things like aldosterone, things like parathyroid hormone. So if aldosterone is around, we're going to reabsorb sodium. Sodium will also have water following it, so that will help us with our blood volume, as we've talked about. But also we can reabsorb calcium. Reabsorbing calcium happens under the actions of parathyroid hormone. Parathyroid hormone, we've talked about in endocrine system and in. But if these hormones aren't around, this doesn't happen. Okay, lastly is the collecting duct. The collecting duct is really important for kind of fine-tuning the contents of that urine. So there's some regulated reabsorption here. So if under the influence of hormones, like the hormone anti-androgen, diuretic hormone. That one's from the posterior pituitary. Aldosterone we've talked about. More ADH. So all of those things can be reabsorbed only when these hormones are around. We'll talk more about this in the next set of videos. But again, I think this picture is really, really great because we can talk about the secretion later. Okay, so we have talked about glomerular filtration. We've talked about tubular reabsorption, and then lastly, we'll talk about tubular secretion. That's the part where we take stuff from the blood, put it back into the nephron. Tubular secretion is basically the movement of certain substances from the blood back into the nephron. Examples of these substances that move from the blood into the nephron are things like hydrogen ions, potassium, this is ammonium ions, creatinine, and then certain acids and bases. But that one is kind of dependent. We're going to talk more about acid-base balance a little bit later. But the major players for tubular secretion are the PCT, because that does most of the jobs, but also the collecting duct. But why does tubular secretion happen? Like, why do we care about it? We just put a bunch of filtrate into the nephron. We just sucked a bunch of stuff out from tubular reabsorption. So why are we putting stuff back into the nephron? And why we care to do this is because we can get rid of stuff we don't want. Things like drugs, toxins, that may be bound to plasma proteins. So if it was bound to a plasma protein before, but now we've been able to kind of separate those things, we can put it back in the nephron. We can get rid of stuff that was reabsorbed in previous steps. Previous steps. The big one here is urea. So we can kind of filter it or reabsorb it out, but then we want to put it back in. But then we also want to get rid of excess potassium. Because too much potassium in the blood can cause issues with membrane potential. So if you have issues with membrane potential, this leads to a whole bunch of stuff like cardiac arrhythmia, muscle paralysis. It becomes a big problem. The regulation of potassium is in large part done by the hormone aldosterone, and that causes tubular secretion of potassium and stuff in the collecting duct. But we can also care to do tubular secretion because we can control the pH of the blood. I'll zoom in on this part. I'm going to star this because we're going to come back to it later. But the example that the textbook goes into, if we're too acidic, we want to get rid of some of that acid, right? And where we can get rid of it is in the urine. So if we're too acidic, we can release hydrogen ions into filtrate via tubular secretion. If we get rid of hydrogen ions, then that also increases bicarb in the blood because we got rid of hydrogen ions from the blood, but we hold on to bicarb in the blood. Holding on to bicarb then increases pH, so we're no longer acidic. If we are too basic, pH is too high, then bicarb can be released in urine. It's kind of like the opposite thing. But again, more on this later because we have a whole lecture for it. So that's tubular secretion. So there's three main jobs: glomerular filtration, tubular reabsorption, and then tubular secretion. And then all of that leads to the formation of urine.